Right, I'm going to get started. Okay, so hello everybody, and thank you very much for coming to my first ever tech conference presentation. My name is Rebecca Rushforth, and I'm going to be talking about 5 years of serverless Java in production, experiences from the Met Office. So the Met Office is the UK's national weather forecasting centre, and we do lots of different things to do with weather and climate, aviation services, space weather, education, outreach, research. But if you're based in the UK, then hopefully you've heard of us because of our daily forecasts and our weather warnings. And there's a weather warning from last summer when we had that really extreme heat wave. And I work in an area of the technology department called Hazards and Resilience, where we get information about possible weather issues out to people who need to know about them for safety reasons. We've been running Java serverless for about 5 years now, and it works well for us. So what I want to do is share some information about how we do it and what the challenges have been. It's really easy to love a new technology when it hasn't yet had a chance to cause you pain. But once you've been using it for a while, you get more of a sense of the pros and cons. So why did we go serverless? In around 2017, a decision was made that the Met Office was going to move everything onto AWS, so Amazon Web Services. And up till then, we'd been using on-prem servers, running JBoss with Spring services, mostly Spring Boot. So the first impulse was to do the same sort of thing on AWS, using Elastic Cloud Compute, aka EC2. And this meant that all of us devs were suddenly configuring our own VPCs and load balancers and network interfaces, etc. But some of the services that we needed to redo at this time seemed particularly fitting for serverless. For example, the National Severe Weather Warnings Dissemination Service. Whenever a weather warning is issued, this sends out alerts via SMS and email to vital recipients in the emergency services like Fire Brigade, Coast Guard, also people responsible for national infrastructure like energy. And there's a 5-minute deadline to get this out, and that's been agreed with the government. If something goes wrong, then it's vital that it can be easily understood by someone who's not familiar with the service, because an emergency warning could be issued in the middle of the night. At the Met Office, there are people on duty 24/7, but they won't know our service, so we have to give very clear instructions if we want them to do support. There might not be a weather warning for some time. We might have some nice weather, and the service still has to be ready to go at any moment. It must be able to handle multiple warnings at once. There aren't usually more than a handful on at once, but still it needs to be able to handle that, and has to be cost effective because it's all taxpayers' money. Serverless has many features that are a good fit for this. It runs on request, so it can quickly scale from 0 to 1 to many. That helps with readiness, cost effectiveness, our 5-minute deadline. The concept of serverless, the concept of not worrying, not thinking about servers, is cost effective because it makes the developers' lives easier. We can concentrate on the business logic in our code, and it also makes things a bit easier to troubleshoot. But it's been using Lambdas with AWS Step Functions that's been especially successful for us, and we use these to orchestrate the interactions between different Lambdas. So, step functions are a way of linking together a series of steps, and the diagram on the right shows the step function for handling a new weather warning. The JSON gets passed down between the steps so that the output of one step becomes the input of the next step. Most of the steps in this example are lambdas, but there is a choice there where it looks at the output of the previous step and skips to the end if there's nothing that needs sending out. So step functions can actually do much fancier things than this. They can manipulate the JSON that gets sent around, for example. But on the whole, we decided to stick with quite a straightforward execution pattern. And we've used them, it's a little bit like a really simplified version of the actor pattern, where you've got immutable messages being passed between separate bits of code, which act on them. Because step functions give a very clear way to orchestrate the interaction of our lambdas, that makes it really easy to split our code up into lots of separate services, each of which is one self-contained piece of work. So we can take advantage of the microservices concept of code that fits in your head. I don't know if you can see that this lambda is called, that step's called Customer Preference Retriever, and it is a lambda, and its sole responsibility is to work out a recipient list based on where in the UK the warning affects. So each lambda in the chain is only responsible for a small, clearly defined piece of work. And one small task per lambda makes it easier to test them, to understand and maintain them. It also means we've been able to reuse some lambdas where they fit into other workflows, or even completely replace a lambda when functionality is needed changing. So if we look at the first two steps, you can see that the output of the warning retriever goes in to be the input of the instruction creator. And the obvious way to handle this is to define a POJO, or at least before Java 17, to make sure that the two match up, taking advantage of Java's type safety. And all of those POJOs can then live together in a domain library. And then they can be used by all the Lambdas and control the format of their communications. So we organize our code in a single repository as a multi-module project. And there's an extract from the Maven POM. This is actually something that we changed over time. Originally, every Lambda was a separate repository. But we tried doing this multi-module thing on some different services and then came back and changed this. Bringing them together has worked a lot better. It's made building and deploying easier. It's made it easier to introduce new devs to the system. You can have a README for the whole thing. But especially good is being able to keep the infrastructure as code in the same repository. So there you can see the YAML definition of the step function, and that's really defining how the Lambdas are linked up, and you can see the link there between warning retriever and instruction creator. If you look at the old world of monoliths in one massive code base, that could be really hard to follow and understand. But when you split it up into separate services, sometimes it's really easy to lose where the connections between the code were. So keeping the infrastructure as code together with the code in one place makes it a lot easier to keep track of what's going on in the system as a whole. So dependency inversion is the D in the solid design principles, and it's a pretty standard practice. But if you have ever worked on a repository, a code base that doesn't have it, you've probably really felt what its benefits are. To recap in brief, it's about making your code depend on abstractions, not on concrete implementations. This also requires separating out creation of dependencies from their use. And there are quite a few different dependency injection frameworks out there to help with this, most famously Spring. Now, before we went serverless, we were using Spring Boot, but we decided for our serverless code to implement do-it-yourself dependency injection instead of using Spring or another framework. All of these Lambdas vary quite a bit in how much code they contain, but like the small ones only contain like a handful of classes, like maybe 5 or 6. A full-on framework seemed excessive for this. It also enables the Lambdas to start up more quickly. And on AWS Lambda, you deploy a fat jar with all the dependencies that are needed, all the required libraries. When the Lambda task is assigned to a server, it has to copy it down to where it's going to be run. So you want to keep your deployable small in size. And I also think the DIY dependency injection is a bit more readable in a small code base. It's also easy to adapt if a Lambda is being reused. So we do this with a very simple pattern with just 3 classes in it. Every Lambda has a class which is responsible for the business logic of that Lambda. The idea is that this class and its dependencies shouldn't care where they're running. They don't need to know they're a Lambda. They could be running anywhere. And then conversely, you have the class which fulfills AWS's API for a Lambda. When a Lambda started, the noargs constructor of this class is called, and then its specified handler method. The Lambda handler has something that can supply a business controller, a fully configured one with concrete implementations for all the dependencies, and that's the only place in that class where any object creation happens in the application. So the Lambda handler is responsible for getting a configured business controller and then delegating to it. Although it's new for us, it was a new thing for us to do our own dependency injection. This sort of pattern's carrying over something we used to use before, and that's what's known as the hexagonal architecture, or ports and adapters, or onion architecture, which also has quite a lot in common with what Bob Martin has called clean architecture. So in this pattern, there's a very thin layer of code on the outside of the application, which deals with its interface or interfaces with the outside world, and the application logic lives inside, isolated from outside requirements. So this has worked well for us in previous code, so we carried the concepts over to serverless. And these decisions have also helped us a lot with testing. People often talk about serverless code being harder to test, but I don't think we found that to be especially the case. Obviously, we have a lot of unit tests because writing unit tests can be a really good exercise for improving your code as well as verifying it. But we also have code at 2 other levels, component tests and end-to-end or integration tests. So we have component tests for each Lambda. They cover the whole of the application except for the thin outer layer, which connects with the outside world. And they use mocks for anything external to the application. That means, like the unit tests, they can be run as part of the build. So the unit and component tests can be run very easily by developers and testers or whoever. We also have a barrier set up in GitHub Actions so that if any tests fail, a branch cannot be merged. Now, we also like to define those component tests using behavior-driven development with Cucumber and Gherkin. So if you haven't come across this style of testing before, it involves writing tests in a sort of English in the form of given, when, then statements. Then you write step definitions to translate the tests, translate the English into code, and you can reuse those step definitions in other tests. There are two really big advantages here. The first is it makes it really easy to share these definitions and tests with non-devs, like, for example, product owners, other stakeholders like that. And they also act, though, as a sort of executable documentation, which is intrinsically cool. There was an occasion when a service manager came to me and asked for some very specific details of the logic of a Lambda, which I hadn't looked at for literally years. And I was able to send her the Cucumber, which exactly defined what she needed to know precisely. But even better than that, before I sent it to her, I was able to run the Cucumber to test that nothing had been changed, because it's always the problem with documentation, that it can get out of date. So this sort of executable documentation, it's very pleasing. You might forget to update the docs if you're in a rush, but that's less of a risk if they're making your build fail. So the other tests are integration tests. These are automated tests for the deployed system. They are both end-to-end tests because they test standard pathways through the system, and they're integration tests because they test integrations with other components and other services. We keep these in their own module in the code base, and we run them with Maven as integration tests. So they start by running setup, which replaces the external dependencies with mocks. This warning service, it has two inputs, one about warnings and one about customer details, and it has one sort of output place, which is the API for sending emails and SMSs. So the tests work by changing some environment variables for Lambdas so that it can have mocks controlled by the tests, and our output can be captured, so that then when the tests run, they change the inputs and check that you get the right outputs, as usual for tests. These tests are also written in Cucumber, and that's because of all the benefits that I mentioned for the component tests. We run the integration tests as part of our deployment pipelines. We use AWS CloudFormation for all our infrastructure, and our deployment pipelines run on Code Pipeline and Code Build, which are AWS specific. So they're always run every time we deploy to a dev environment, and they fit into our main deployment pipeline, as you can see here. They're run on a CI environment before deployment to staging, which is followed by a prod approval. When I was writing this, I was sort of trying to think of where we'd made our worst mistakes. Definitely there have been times when writing these integration tests has been pushed by time constraints, deadlines, ended up sitting on a backlog instead of getting done at the same time as the system. And the problem with this is that tests are so much easier to write at the same time. And any subsequent maintenance is much, much easier if you've got the tests in existence. Small things like changing build configuration, or updating the dependencies, anything like that. It's much more straightforward if you can make sure that there hasn't been some sort of inadvertent change to the essential behavior of the system. And they're useful for people who don't know the system well. So I would really recommend having these sorts of tests. They've been really, really helpful for us. They take time to set up, but they will increase your efficiency in future and contribute to the reliability of the system over the time. So a very big bonus for us of using step functions is that they actually have a really good GUI. It sounds superficial, but it's very important, really. Very helpful when deving, as well as for troubleshooting and support tasks. This is a screenshot of a step function. It's on a dev environment, and it's just run some integration tests. You can see there's a list of all the executions there have been, and at the bottom there's one that's failed. So you can click on a run to get details about that execution. So there's the one that failed. You can see the top of a diagram there. I'm going to move on to a screenshot that shows you the whole diagram. So you get a diagram of the run with the steps color-coded according to how they went. You can click on any specific step to see the input and output of that step. Really helpful for debugging. And you can see what went wrong in any step that did go wrong. There's also these links which will take you straight to the Lambda definition or to the logs. If you've used CloudWatch logs in AWS, you'll know it's really helpful to have something that will take you to the right log group instead of having to sort of go and look for it. It's also extremely supportable extremely useful for writing support playbooks. So This is the same execution that failed, but I've switched to this tab which shows you the execution input and output. If you click on the new execution button at the top right, it gives you the option to start a new run with the same input. And then it gives you the chance to change the input if you want to and give it a specific name. This is really useful for writing straightforward support documentation for people who might not know the system. We can tell people that a specific error means that it's worth retrying that run, and we can give them really clear instructions on how to do it. These might be people in the middle of the night who are stressed. They don't know the system, but they know that it's a system that affects people's actual safety. So anything that makes that situation less stressful for everybody is really helpful. So I've only really had time to talk about one of our services here. Most of our others are very similar. You'll notice that startup time for Lambdas is not an issue for us in these really simple event-driven systems, which is obviously different from if we were running a RESTful API. But there are some possibilities for decreasing start time, which are interesting. I don't have time to talk about them. Another trade-off is the issue of vendor lock-in, especially the case for step functions. However, in summary, this architecture has worked really well for us, giving us services we can maintain, understand, support, and adapt as required. Thank you very much. It would definitely be way more expensive for us because we have really, or most of our services have massively important, must be supported services which don't have a massively high volume, but they're used in critical situations, if you see what I mean. Like we've got surface water flooding stuff where we've got like maybe a handful, like 2 or 3 users, but those users then make documents about flooding and warnings about flooding that are used by the whole country. So it's about, we don't have that situation of really high volume. So if we can get a win in terms of supportability at like, and we're talking a very small cost. I mean, I think the weather warnings cost something like $40 a month or something. Like we're not talking a massive cost. It would be a false economy to, you know, make life harder to support in order to save a few cents, probably. Yeah, cheers.